Okay, for problem 8, we're asked to find a power series representation for this function, natural log 1 plus x to the fourth. So the way that we're going to do this is we want to use the power series representation for 1 over 1 plus x. And that is this, as we've seen. N equals 0 there. If we remember from our geometric series, this is the same as 1 over 1 plus x. Okay. So in order to use that, we need to somehow figure out a way to make this function, or perhaps its derivative or integral, to look like that. And so the way we do that is we realize that the derivative of the given function is 4x to the third over 1 plus x to the fourth, which kind of looks like this, and we can actually use it to form a power series, at least for this. And in order to do that, we'll have to rewrite this as 4x to the third times 1 over 1 plus x to the fourth. Then we will look at just that, the 1 over 1 plus x to the fourth, and realize it looks almost exactly like that. So we can use the composition rule for power series and just replace that x to the n with x to the fourth. So this will look like minus 1 to the n, x to the fourth to the n, which actually ends up being x to the 4n. Okay, so that's the power series for this, and so the power series then for 4x to the third multiplied by that is what we want next. So we can say, so 4x to the third times 1 over 1 plus x to the fourth must be equal to 4x to the third multiplied by the power series representation of this, which is, we just said that, so minus 1 to the n x to the 4n. And remember that when we've got a power series multiplied by something like this is just a bunch of things added together, so this can just sort of be distributed in there. And so we'll get 4 times all of this, and then this x to the third gets multiplied by that, so we're going to be left with x to the power of 4n plus 3 there. So basically just adding these exponents on the x. So this is the power series, again, this is the power series representation for the derivative of the function that we started with. So what we want, though, is not that. We want the power series representation of this one. And so how do we get back to that one from what we just did? Well, we took a derivative to get here, so we have to take an integral to go back. So the power series representation for this one must be the integral of what we just got there. There's a constant, so we can put the constant out in front. We're going to integrate this power series. Okay. And then remembering that when we integrate a power series, this is just a polynomial, so we can just simply use the power rule to do that. So antiderivative of that thing, we'll get minus 1 to the n. Raise that by 1, so we get x to the power of 4n plus 4. Then we divide by what we have in the exponent, so 4n plus 4 there. And then we'll have a constant attached to this. Then you can notice that you got a 4 in the denominator there, so you can actually factor that out, and it will cancel with the 4 that's there. So what we're left with after all this is x to the 4n plus 4 over just n plus 1 after the factoring of the 4 out and canceling. Okay, then we can also determine what c is, because if you notice, f of 0 on this thing is what we get when we plug in 0 there. If I plug in 0 there, I get natural log of 1, which is 0. And so that should be the same thing that I get when I plug in 0 to this thing, forgetting my c there. So if I plug in 0 here, notice what I get. F of 0 here would be plugging in 0 there. So I basically just have 0 to any power is 0. So this is just going to be a bunch of zeros added together. So f of 0 here is 0 plus c. And so that tells me that c must be equal to 0. So my constant is 0 in this case. And so my power series representation of the original function then is this. And this one doesn't ask for interval of convergence. But if it did, we would know that this thing that we started with has this for its interval of convergence. And so by integrating, we actually may end up including an endpoint here, but since this thing doesn't even ask for the interval, we're not going to concern ourselves with that. So this is what we need right here for our final answer. And on the test, since I didn't ask for interval of convergence on this particular problem, I wouldn't ask for it on the test either, so this is good enough. Although, as I say in the solution there, that is what the interval of convergence is.